Okay, so today we're going to talk about the following theorem. So this is a theorem, it's in the handout, but let me write it out. So G be a finite group. And okay, just let G be a finite group, and we're going to work over the complex numbers. Then the characters, well, yeah, let me say it this way. And let me fix representatives for the irreducible representations. So let V1, Vm be representatives for the irreducible, the irreps of G over C, so over the complex numbers. Then the characters, chi V1 through chi Vm, are an orthonormal basis for, well, okay, so it has to be for a vector space with an inner product. So let me say what that vector space is. So for the space of conjugation, let me say it this way, conjugation invariant functions on G. So let me just mark, we often call these class functions, or you could sort of just think of them as being functions on like the set of conjugacy classes in G. But they're just, here it'll be more convenient to think of them as being a function that's a function that's sort of defined on all of G, but just constant on the conjugacy class. So, and we saw last time that the trace is constant, like the character is constant on conjugacy class just because the trace of a matrix doesn't change if you sort of conjugate the matrix. Okay, so that's the vector space, conjugation invariant functions on G. So this is not complex conjugation, by the way, this is conjugation in the group. And then with inner product, well, if you have two functions f and g, then the inner product is just 1 over the absolute value of g, the sum of f of g. And how do I want to write this? Let me write this as f bar of g, and for f bar up, we call the functions f and h, and then I'll call the elements my group G. So I'm summing over all the elements G and G, and I take the value of f of x on the complex conjugate of, I'll take the complex conjugate of the value of f and G and multiply it by the value of h of G. Okay, so this is a Hermitian inner product. So it's easy to check. I mean, it's just sort of the standard Hermitian inner product in sort of a certain basis. You can sort of think about what that basis is. So this is a Hermitian inner product, which is sort of conjugate linear in the first variable. So depending on your conventions, you might take a Hermitian inner product to be sort of conjugate linear on this, the first variable or the second variable. Yeah, well, okay, we could do either way. Well, I think, okay, I'm used to doing it the other way, so let me do it this way, and I'll just change what I'm going to write later this way. Okay, so we'll have it be conjugate linear in the second variable. Sorry for the confusion. Right, so, okay, that's the theorem. This says we have a finite group, then if we fix representatives for the conjugacy classes, then the characters of those, if we fix representatives for the irreducible representations of G, then the characters of those irreducible representations give you an orthonormal basis for the class functions, where you have sort of the specific inner product. So let me say some corollaries of this before we prove the theorem. So one corollary is that this gives you a precise count for the number of irreducible representations. So how does it do that? Well, the dimension of, so I'm going to write CG, so this is class functions on G. Well, this is just equal to the number of conjugacy classes. You can just take sort of the indicator function for each conjugacy class as a basis. That's not a corollary. And so this is the corollary and the proof of the corollary in one sentence. So this is the dimension of the class function is the number of conjugacy classes. So the number of irreps, sort of up to isomorphism of G, is equal to the number of conjugacy classes. So this is because I said, what did I say? I said this was an orthonormal basis for this vector space. It's not just they're orthonormal, but they really form a basis. So they really, and once you know they're orthonormal, that gives you linearly independent. So just that they actually span the whole space. Good. So you get sort of the number of those things has to be the dimension of the space of class functions, but that's just the number of conjugacy classes. Again, just because you can take as a basis, just like the indicator function for each conjugacy class. And another way to think of this is like this is sort of this kind of representation we've been thinking about before. This space of class functions. This is just Cx, where x is equal to G with the conjugation action. So we saw in general, like whenever you have a G set and you sort of take this representation built out of it, then the number of orbits is, the number of orbits is equal to the dimension of the invariance. This is, it's not supposed to be Cx, it's supposed to be Cx. G, it's the invariant functions in here. Okay, just to connect it to what we have done before. Okay, so that's one corollary. Another corollary is that see the sort of if V is, let's say if V is an irreducible representation, then the multiplicity, actually, we named the irreps, so let me, so the multiplicity of the irrep VI, sort of from this list above, in any representation is just the inner product of the character. Let me do it. And it doesn't matter which order you put this in, but let me put it in this order. So it's the inner product of W with chi of VI. Okay. So I proof this corollary. Well, W is equal to sort of V1 to the M1. So W is isomorphic to V1 to the M1 plus V2 to the M2, and so on. to V, so the M to the, so I better call these multiplicities Ks, V1 to the K1, V2 to the K2, up to Vm to the K sub M. And so then chi of W is just K times chi of V1 plus K1 times chi of V1 plus K2 times chi of V2, so on, all the way up to Km times chi of Vm. And so that's just using that the character sort of adds up over direct sums, which was again just because the trace of the matrix sort of adds up over direct sums. Good. So then if we look at W chi of Vi, well, now we've sort of expressed, we expressed chi of W, I wrote W. So if we look at the inner product of chi of W with chi of Vi, well, we know that sort of every time I sort of pair one of these irreducible representations, if not the ith one with this guy, I'm going to get 0. That's what it means to be orthonormal. And when I pair sort of the ith one with this, I'm going to get 1. And then I'll just sort of pull out the coefficient in front. So this is just going to be equal to Ki by orthonormality. And this Ki is exactly what you mean when you say the multiplicity of Vi in W. Okay, so that's a corollary. Let me give another corollary sort of based on this. And it's fun, you can sort of stack up, you can just stack up a lot of things all at once. This is a very powerful result. So the dimension of the multiplicity of Vi in the regular representation is equal to the dimension of the Vi. So in particular, that implies, and I'll spell out the implication, that the sum of the dimensions of the irreducible representations, if I square those, is equal to just the size of G. So I take the sum of the squares of the dimensions of the irreducible representations, then I get G. I get just the size of G. So that's sort of some pretty precise numerical constraint. Before and let me add one more statement. Sort of in particular, G is abelian if and only if sort of all its irreps are one-dimensional. Okay. So let me just say why this in particular holds. Well, we know the number of irreducible representations is the number of conjugacy classes. And so, well, the number of conjugacy classes equal to sort of the size of G if and only if the group is abelian. But then, like, the only way you can sum sort of right. So, and if you have G, if you have G size of G order of G conjugacy classes, then sort of this sum is over order of G irreducibles, sort of by this correlate. It's the number of conjugacy classes, and then sort of something squared. But if you're getting this order of G, like each of these can only be 1. On the other hand, if you have fewer, and if there's any conjugacy class that's not just a single element, so if you're not an abelian group, then there are sort of fewer terms over, like there are not G terms over here. There are fewer than G terms over here. So one of them is going to have sort of be larger than 1. So that's sort of where this last in particular comes from. And let me just do an example before we prove the corollary. So the irreps of S3, well, we've already seen 3 irreps, and you can sort of check they're different. So they're the trivial representation, they're the sign representations. These are one-dimensional. So these are just the characters of the group. Characters in the sort of the traditional, in the previous sense, whereas the multiplications maps to C cross. And then there's the so-called standard representation. So this is contained in sort of this permutation representation on the set 1, 2, 3. It's sort of the subspace of the x, y, and z such that x plus y plus z is equal to 0. So we'll check in a moment that that's, so I'll give you another way to check in a moment that that's irreducible. But for now, actually, maybe we'll do this as an exercise in class. But okay, good. So and these are the 3 irreps, and well, they have this one-dimensional, and this one is 2-dimensional. And if you know these are 3 irreducible representations and they're all distinct, well, definitely the trivial representation and the sign representation are distinct, and then this is 2-dimensional. So if you know it's irreducible, like you're done. Because then there are only 3 conscious classes in S3, so you know that's sort of all of them. But then also you can check, I mean, the sum of their squares, their dimensions is also equal to that, is equal to 6. So 1 squared plus 1 squared plus 2 squared is equal to 6. Okay, so, and this is just an example sort of illustrating some of the numerics that we've written down. But let me say the proof of the corollary. Well, the character of CG on an element G, well, that's just going to be equal to the number of sort of fixed points. So this is something we saw in the exercise session. This is the next number of fixed points of G acting on G. So this CG, this is sort of, you're thinking of G as a G set by a left multiplication, But that's just everything if G is the identity. So that's, and otherwise it's nothing. And there are no fixed points if G is not the identity element. Okay, and sort of sends every group element to sort of G times that group element, which is G is not the identity. By cancellation, that's not the same element anymore. Okay, good. So this is the character of the regular representation. And so we get that the multiplicity of VI in CG, well, it's equal to inner product, this representation with VI. Sorry, inner product these characters. And I mean, knowing nothing about the character of VI, we might be worried that this is going to be hard to compute. But, and we do know one thing about it, we know sort of what it does in the identity element, and that's going to be enough, because if you look at sort of the sum, here's taking the sum over all elements of G of the first character, evaluate it. G times second character, evaluated G, and conjugated. But by this computation we just did, like this is going to be 0 if G is not the identity element. So we just only are left with chi G. And then when we get the identity element, when we get that identity element in the sum, we're getting, well, just the size of G from this term when we have the identity element. And then this other term is giving us, well, chi vi G of the identity element. Or these 1 over G's cancel, and then we talked about this last time very briefly when we introduced the character, but the character of the identity element, well, that's just the trace of the identity matrix. So this is equal trace of identity matrix on sort of a dim VI dimensional space. So, well, that is just the dimension of VI. Okay, so that means, yeah, so, but and what we were computing was this inner product, which sort of by the corollary, by the corollary above, so the multiplicity of VI in any representation W is just given by this inner product. So, great, so that means, so that's, yeah, I think that establishes the first part of what I said. So the multiplicity of VI is the dimension of VI in this regular representation. But now we want to get this numeric result, but we just get that by adding dimensions, because now CG is equal as a vector space to the direct sum from I equals 1 to M, so over our irreducible representations of VI, and then each VI appears dimension of VI times. So, okay, so the dimension of that, the dimension of the left-hand side, is equal to the dimension of the right-hand side. And the dimension of the left-hand side, well, that's just the order of G, so the size of G. And the dimension of the right-hand side is, if I look at the ith term, I get the dimension of VI, sort of dimension of VI times, that's sort of dimension of VI squared. Okay, and then I already sort of went over how to get this last part of the corollary, that's in particular, G is a Boolean if and only if all the erupts are one-dimensional. But okay, and so I want to point out, like, sorry, a little bit already in this example, but this is, you have two very powerful, like combined, these two constraints are actually very powerful already just for like classifying irreducible representations of a group. The fact that you know how many there are, there's sort of the same number of irreducible representations as there are number of conjugacy classes, and you know the sum of their orders squared is equal to the order of the group. I mean, like, if you take a number, like, there aren't always that many different ways to write it as a sum of squares. So sort of you can often get quite a bit of information about what the dimensions of the irreducible representations are without sort of doing any work towards constructing them, just by sort of these two numerical identities. Okay, and then this was just sort of a simple corollary of the fact that these characters were an orthonormal basis. Okay. So yeah, so let me sort of scroll back up and just go over. So we had this theorem that said, if you look at the class functions, the conjugation invariant functions with sort of this inner product, then the characters of the irreducible representations are an orthonormal basis. So we haven't proved this yet. We're going to do that in a second. But then we just sort of got these nice corollaries. We got the number of irreps is just the number of conjugacy classes. We got that we sort of compute the multiplicity of any irrep and any other one using this inner product of the characters. So like this is somehow a very computable way in which you can decompose representations into irreducibles if you know the characters of the irreducibles. We got so this, and then we got just by applying this to the regular representation, we got this nice result. So this nice numerical control over the sum of the squares of the dimensions of the irreducible representations. Okay. Good. So let's do the proof of the theorem, and we're going to split it up into 2 steps. So the first thing I want to do is prove of orthonormality for the characters. Okay. And so yeah, so okay, so I'm going to sort of do something. So, and yeah, this is going to follow from an identity we already wrote down. So this is going to follow from yeah. So I'm going to prove the orthonormality first, and then we'll prove second. We'll see how long this takes, and then if we have time, we'll finish the proof that they span. Otherwise, we'll finish that next time. But so, and that's the 2 things we have to prove. We have to prove the characters are orthonormal, and then to see that it's a basis, you have to sort of prove that they also span the whole vector space of class functions. Okay, so right, so this is going to follow from the fact that the G homomorphisms from V1 to VI, so this is either equal to K if I is equal to J. So it's just sort of the scalars. If I'm just looking at maps from one irreducible representation to itself, or 0 if I is not equal to J. So this is something we talked about last time. This is like the basic property of irreducibles. In complete sorry, this K is C. So in complete generality, sort of the second thing holds, and then sort of you'd get sort of some division algebra when I is equal to J. So this basically comes from VI to VJ. You get some division algebra when I is equal to J. But Schur's lemma, which applied over an algebraically closed field, and particular complex numbers, says you just get C in this case. Okay, so we're going to use this, and then we're going to use the fact that this is the space of G invariants in Hom VI to VJ. So, so in Hom VI to VJ, this is equal to, as a representation, so if I write sort of rho I for G to GL of VI, then rho sub the action of an element in G on a linear transformation. So yeah, so this stacks up a little bit, so it gets a little bit confusing if you're not thinking carefully. But I mean, this, so I'm saying sort of the space of homomorphisms from VI to VJ is naturally itself a representation. And so the action on some linear transformation phi, the action of G on some linear transformation phi is just, I take phi and I precompose with rho I of G inverse, and then I postcompose with rho J of G. So I think I wrote this down in the first lecture on representations, but good to have it again. So in particular, and this is sort of the natural action on functions. And in particular, like sort of saying you have something G invariant here is exactly sort of saying you can move the action through. Sort of acting on the right is the same as acting on the left. And if you think, if you're wondering about this inverse here, I mean, it's just sort of to make, and somehow when you compose on the inside, like your directions get swapped. And so you need to sort of get an inverse here. Otherwise, like your left and right multiplications sort of aren't going to stay in the right direction. Okay, so that's the definition of the action on here. And sort of anyway, the point is that the space of G invariant homomorphisms is sort of the space of G invariants in just all linear transformations with this action. Okay, now there's another way to write this. Because Hom VI Vj is just the dual of Vi tensor with Vj. So this is true always for vector spaces. Like, and so this is just linear transformations from Vi to Vj, and there's a canonical identification with this, and sort of, and this identification is described on simple tensors just by, so if I have little Vi dual, so this is something, some tensor, some functional on Vi. If I have the simple tensor where I have sort of some functional tensor with, let me sort of just write this. So let me write this for general vector spaces. So I don't sort of get the notation too confusing, these different letters. So this is something completely general, this equality for vector spaces. So Hom A, B, so A and B are vector spaces, is A dual tensor B. And where the identification is given by sort of a functional on A, tensor B. So this is a simple tensor, and then everything in this tensor product is a linear combination of these simple tensors. So we just sort of extend by linearity. Well, you don't extend by linearity, but there's sort of an extension by linearity that agrees with this. I mean, this is sort of a subtle point. And of course, like what a map from the tensor product does on simple tensors completely determines the map. People often make the mistake of sort of trying to write down a map and claim it exists by sort of writing down what it does on simple tensors and sort of. But of course, then you have to check something. You have to check sort of that that's compatible with. Well, okay. If that didn't make sense to you, you should probably think about that. But anyway, I'm not sort of saying I'm defining the map. I'm just saying there is a map, and you can check it yourself if you haven't seen this before. But so this A dual tensor B just maps to the thing that sends an element A in capital A to sort of A dual of A tensor B, or times B. I mean, A dual is just an arbitrary element of A dual, and sort of A is just an arbitrary element of A. So there's no relation between A dual and A here. It's not like I haven't like fixed a dual basis or anything. So this is an identification between these two vector spaces, but the point is sort of if these both have representation of G, then this as an identification sort of as G representations. So this tensor product representation sort of matches up. Okay, so good. Yeah, so what did I want to say? Right, okay, so now the point is we have a projection operator onto the G invariance. So we have so this is something we've used already, and this exists really for any representation. So this is just the sum. Okay, so let me say this sort of for any representation V. It's just the sum over all G and G, normalized by 1 over the order of G of rho of G. Okay, so you add up these linear transformations. So each row of G is sort of a linear transformation of V, and so you just add up those linear transformations and you sort of divide by the order of G. So this is sort of containing an end of V. So this is true for any representation of V, and we applied sort of this averaging idea when we applied this averaging idea already to sort of the space of endomorphisms of a representation when we were sort of trying to to average projection operators onto complementary subspaces, like when we were proving complete reducibility. So this already showed up in complete reducibility. Okay, and so we're going to apply this to so the representation V equal to sort of a Hom of VI Vj. And so we're going to apply to sort of something specific in here to get what we want. Right, so we're going to apply this to okay, so I think I just misspoke a little bit. So I paused the recording to gather my thoughts, and so I'm just going to go back a second to make sure so I said things correctly. So we're going to apply like this formula here for the projection operator onto the G invariance. In this case, where sort of V is Hom VI Vj. So, and the point is, if I take the trace, yes, let me sort of in this sort of generality, the fact that this is a projection operator on the G invariance implies sort of the trace of this operator. Let me write that down here. So, and the trace of a projection operator is just equal to the dimension of its image. I mean, a projection operator literally, so you can sort of write the vector space as the kernel, as the direct sum of the kernel and the image, and then like if you sort of take a basis for those two summons, then like the projection operator is just the identity on the image, on sort of the image as a direct summand, and sort of 0 on the kernel. So the trace of a projection operator is the dimension of its image, and so you get sort of that the trace of 1 over G, and the sum over G containing G of rho G. So I'm just adding up sort of linear transformations rho G, and I'm averaging them, and then I'm taking the trace, which is equal to just 1 over G times the trace, the sum over G and G, just using linearity of trace of rho G. which is rewriting. That's just 1 over G, the sum over G contained G of the character of rho evaluated G. Okay, so this is starting to look pretty good. And then, so that's sort of how you compute the trace just by expanding out. But on the other hand, like we know that this is the image of the dimension of the image because it's a projection operator, and the image is the G of variance. So this is the dimension of VG. So this is sort of for an arbitrary V. So now, but let me sort of plug in V is equal to Hom VI Vj, which I can also write as VI dual tensor Vj. So then on the left, I'm getting the dimension of the G invariant homomorphisms, VI to Vj. And so this is equal to 0 if I is equal to J, sorry, if I is not equal to J, because then it's sort of 2 distinct irreducibles, so there's no mass between them, or 1 if I is equal to J. Okay. And that's Schur's lemma. So again, this is this fact we recalled earlier. So that sort of tells you what the answer is going to be. And then the key thing is sort of expanding out what this formula gives you. So this is equal to 1 over, and okay, so to get sort of the answer, I use this interpretation in terms of homomorphisms. Get the formula, I'm going to use an interpretation in terms of tensor products, because this is 1 over G. And then the tensor product of 2 representations, the character of the tensor product, recall, is the product of the characters. So this is just the chi of VI dual tensor chi, or times chi of VI of Vj G. And then there's this thing I mentioned at the end of the exercise session, and that we'll talk more about in next time's exercise session. So whenever you have a character, like when you have a representation of a finite group on a complex vector space, like, well, the eigenvalues of sort of the matrix are roots of unity. But that means sort of the trace of the dual matrix is just going to be sort of the conjugate of the trace of the matrix we start with. So that means the character of VI dual is just the conjugate of the character of VI. So yes, let me then also swap the order. So this is chi of Vj G times chi of Vi G complex conjugate. I just swapped the order to emphasize the relation with the inner product, because this is exactly the definition of the inner product of chi of Vj with chi of Vi. Okay, so this says the inner product, and this formula now says the inner product of chi of Vj with chi of Vi is 0 if I is not equal to J and 1 if I equals J. That's exactly the statement. These sort of functions are orthonormal. So just, and to recap, let me go all the way back to the statement for the theorem. So for finite group, we were proving that the characters of the irreducible representation, we wanted to prove that they are an orthonormal basis. So in step 1 is prove they're orthonormal. And I think that's where we'll stop with that proof today. So we'll come back to the fact that they're a basis next time. But so we wanted to prove they're orthonormal, so we have to compute sort of the inner product of them. And the key point was that, like, I mean, somehow this statement that they're orthonormal is just a rewording of this computation we already did, that just sort of followed from the definition of irreducibility and Schur's lemma, that like the space of Homs, between the space of G invariant homomorphism between 2 irreducibles is 0 if they're not isomorphic, and just one-dimensional if they're isomorphic. And so then we reinterpreted that using the fact that when to prove them, we then use the fact that sort of these G-invariant homomorphisms were the space of G invariants in some other representation, which sort of is all linear transformations has a natural G action, and sort of then the G-invariant homomorphisms are just sort of the G invariants in that representation. And then moreover, that sort of we could write this representation in two different ways. We could write it sort of as the homomorphisms, but then we could also write it as the tensor product. And so sort of writing it as the tensor product sort of let us sort of compute the a character that was showing up in terms of the characters of VI and the characters of VJ. And then writing it as sort of this homomorphisms let us relate to this result here. Okay, and then sort of the trick, as it has always been in representation theory, like every result we proved, is then to apply a projection operator. So we project onto the G invariants, and then we know that we use the sort of the trace of a projection operator is just the dimension of its image. And so we have sort of this formula for the projection operator. And so we get that the dimension of the G invariants in any representation is sort of the sum over that, this sort of the sum of the traces of the elements. Yeah, and by the way, and this is like something we sort of saw also in sort of the examples of representations coming from G sets in the exercise session, this identity. So this is true more generally. Good, and then we just expanded sort of this left-hand side for, again, sort of was the Schur's lemma equality. They gave us this was 0 or 1, depending on whether I was equal to J or not. And then on the right-hand side, we just expanded it out using sort of this tensor product representation, the fact that characters multiply in tensor products. Good, and then we expanded it out, and then we got the inner product. Right? Okay, and so that's the end of the proof of orthonormality. And right, and so just recall, so it remains to show the chi-vi span the space of class functions. So that will be next time. Okay, thanks, and I'll see you guys in class on Thursday.